We'll finish up section 7.6. This is over the translation theorem. So we're going to solve a few IVPs and then talk about the derivative of the Laplace in this video. Okay, so I wrote a couple things down. These are from table. You would have to identify these when we need these here in a little bit. So I just wrote them down, save us some time of having to reference that these two Laplace transforms are going to be used in this problem. Okay, so first thing we always do is we want to say let the Laplace for y of t, we want to give it a name, capital Y of S. All right, then I like to write this to let the reader know what I'm about to do. I'm going to take the Laplace of the dE. Okay, so we get the Laplace of y prime minus the Laplace of y equals the Laplace of t e to the t sine t. All right, this over here is not too bad. It's going to be s to the first power times big Y of s minus s to the 0 power times y of 0. Minus, okay, that's just big Y of s. All right, this one, we have quite a bit going on here. Okay, so this t, e to the t is going to just put a s minus 1, and anywhere there should be an s. Okay, t sine of t, we have it up there at the top. So this is going to be 2 times, and instead of s, because the e to the t, because this is a 1, right, I put s minus 1. The 1 here tells me to put s minus 1. Over, right, I have s minus 1 squared plus 1 squared. That e to the t caused all the s minus 1s. Right, now I solve for big Y of s. I'm going to factor it out. There are two terms here. We get s minus 1. Y to the 0, thankfully that's gone. It's just a 0. That came from here. Equals 2, and I don't multiply anything out until I know I have to. Save time, and then also things are going to go away here. Okay, s minus 1 squared plus 1 squared. I divide both sides by s minus 1. You can see why I didn't want to multiply that out, leaving me with 2 over s minus 1 squared plus 1 quantity squared. All right, now we are down to a big Y of s that looks familiar. That, if you look, I'll scroll out, that is that top one there. So if I take the inverse Laplace of both sides, I get y of t equals, right, the inverse Laplace of that looks just like this, where k is 1. So I get sine, the s minus 1 here goes where this s was. So we are working backwards, kind of like what we did here to here. We're going to work backwards now. So I get an e to the 1t because it's at s minus 1. So this thing here manifest that. Then I get what was there, sine of t minus t cosine of t. All right, so the s minus 1 manifests that e, and the same thing here. This gave us the s minus 1. Okay, hopefully that's okay. That's how you solve an IVP. This one's really nice. Let's do one that's not as nice. So we did a lot of work in this section and last section about heavy side stuff so we could work with this. All right, a couple of rules that are going to show up. I put them up there at the top so I don't have to reference the table. The first thing I'm going to do is change this piecewise function to a heavy side, excuse me. So I get 1, but then I want to minus 1 away when t is pi over 2. When it's pi over 2, I want to add sine of t. All right, we can put these together then. We get 1 plus sine of t minus 1 times the heavy side t minus pi over 2. All right, this is not as obvious, but this is a trig sub. If you draw a right triangle and think of pi over 2 as 90 degrees, we can easily see, and I'd encourage you to do it, that this, I'm going to do a bracket here, cosine of t minus pi over 2. It is a trig sub. Draw a right triangle and think about your angles, and you'll see it pretty quick. All right, so that all there. The only thing that didn't change or that did change, was I changed sine of t to cosine t of minus pi over 2. The reason I did that is because now I have these matching. That's nice. That's going to help us when we take our Laplace. All right, so let the Laplace of y of t equal big Y of s. And let's take our Laplace. And Laplace of dE. Okay, so we can do that now. Laplace of y double prime plus the Laplace of y equals now the Laplace of all that. So the Laplace of 1, I'm going to put that by itself. Then we have plus the plus of everything in there. If you write big, we're going to run out of room on this page, just so you know. So we get cosine of t minus pi over 2 minus 1 times the heavy side of t minus pi over 2. Thankfully, this is very, like exactly what we worked with earlier, with the heavy side in there and the t minus pi over 2's. So the first thing we get is s squared times big Y of s minus s times y of 0 minus y prime of 0. That's that rule for that. Plus big Y of s, that's the Laplace of y, equals, okay, we get 1 over s, that's the Laplace of 1. And then for this one, because the heavy side and these two things matching, this is how it's going to turn out. We do get e to the negative pi over 2s, then times the Laplace of whatever was inside without it. So we get the Laplace of cosine and Laplace of negative 1. So the Laplace of cosine is s over s squared plus 1, right? And the idea is this is a 1t. If I take away that, that's why it's plus 1. Minus, it's 1, so we get 1 over s. Okay, so the left-hand side, I'm going to put my big Y s's together. I get s squared plus 1. This goes to 0. That's what this says at the beginning. Then I got a minus s here. All right, this just comes down. I'm going to be lazy there. Now I'm going to add s to both sides and divide by s squared. Let's just add s actually first. S squared plus 1. I'm going to add s and do this. S to plus 1 over s. That's, okay, s squared over s plus 1 over s, which means I get s squared plus 1 over s. That was adding s over to the other side and adding it with that 1 over s. Plus, and then I get this mess. This time I will write it. Sorry for my lines not being straight. I'm using an iPad on a shaky desk. All right, there we go. Okay, now I divide everything by s squared plus 1. You can see why I combine like terms on that one, because it's going to make our life nice. Y of s equals, if I divide by that, I get 1 over s. Now the other one I do have to divide by it, so I get e to the negative pi over 2 s times, okay, I get s over s squared plus 1 squared minus 1 over s times s squared plus 1. All right, now we can take our inverse Laplace. So we get, okay, 1 over s, that's a nice easy one. We get a 1. Plus, okay, this is where it's not so clean. So let's look at those rules at the top. They're almost that, if you take a look, each one of them, where k is 1. The only thing that we are missing are the 2's up there. So I could put over 2 here and then put a 2 and a 2 there. Now that actually hits both of those formulas. So take a look at those formulas, make sure you're good. This should be that's a 1. Hold on one sec. There should be, I made a mistake way up here. S squared, it's right here. S squared plus 4 k squared. All right, this one's not totally obvious where to go here. Now, here's the deal about that k, because k has to be something I need to match. Okay, so I'm going to do some pattern matching here. Let me copy this. And we're going to do some pattern recognition here to help us understand this. Okay, so I have that. I don't need this. And I have 2 over s times s squared plus 1. And I need that k there. So s over s squared plus, okay, I need a 4. And then I need times something squared that's going to get me back to a 1. I think that's a 1/2. 1/2 squared is 1/4 times 4 gets me back to that 1. So k is actually a 1/2. So we need to, okay, so we'll have a 2 for that one, but this 2, maybe we shouldn't add that in. We need a 1/2 for our k. 1/2 times 2 is going to be 1. So actually, that works out just right for us. We don't need to add a 2 or anything to this, to that top number right here. That actually matches when k is 1/2. Okay, so we have that. I'm going to erase all this. Now I know that matches. So, okay, the first one, I got that e to the negative pi over 2. I get 1/2. So let's go ahead and do that. 1/2. And then I plug in, this is that rule up here. Here I can copy and paste it so we can have both down here. Okay, so that gets me, okay, remember with the e to the negative pi over 2, that means I have to plug in t minus pi over 2 for each t. So t becomes t minus pi over 2. And then I get sine of, okay, k was 1, but I do have to change sine to t over pi minus 2. That comes from right here. That's why we have to do that. If not, we would just put t's if that wasn't there. Now, we do get the half from there. On the second one, though, we won't have a half because it's already set up for us. This becomes minus sine 2, but now I do have to replace this one because it still has that e to the t. All this is going to be times the heaviside function at pi over 2. That's following that rule. So my answer here is all of that. It's kind of weird like that, but that whole answer. Very strange. For tests, a middle ground for this would be nice. Maybe not. Maybe between the first problem and this problem. There's just a lot going on in the middle there. So take your time. Pattern recognition is difficult. We are just not used to this kind of thinking all the time. We're used to, here's the definition for a derivative. Here's a definition for an integral. Here are the patterns. This is how you find that. The problem with this is you don't have that pattern thing in the middle of where you start working with them. Like your derivative, they were like the power rule and the quotient rule. Your integrals, you had u subs and integration by parts. This one is just like, here's the definition. Okay, you can do it by definition now, but here's a table. There's no like middle ground of like techniques. It's just following the patterns, which makes it very difficult. So be very gracious with yourself. Take your time. Go slow. This stuff is pretty difficult for students. All right, I have one more idea. 2 pages here. Derivatives of a Laplace transform. So we are going, if you follow this, let's follow this rule, this here. I'll just highlight as I go. So that's what this means, right? F prime of S. The definition would just be take the definition of my Laplace transform and take the derivative. But we can move the derivative on the inside. But if I do that, I got to change it to a partial because I got t's also. If we take the derivative now of that inside, e to the negative st, and this isn't even in s, right? In terms of s, it's just t, so I don't even take the derivative. It's a constant if it's a partial. But the derivative of e to the negative st, the negative t comes down, and I get e to the negative st. If I work this out now from here to here, that's what we get. So for the first derivative, we get negative t times f of t. If I follow the same logic, we get here, positive t squared times f of t. If we were to continue, we could probably figure this out, d3 f of ds3. If I follow the same rule, okay, the first one had a negative, this one had a positive, so this probably has a negative t to the third times f of t. Not too bad, right? Same rule each time. Now, if I take that and I extend it towards n, right, some nth derivative, we get this. Negative 1, think about this, negative 1 to the nth power changes the sign. If n is odd, it'll be negative. If it's even, it's positive. And then we have t to the n. That's the power thing going on there. And then times f of t. And then the Laplace of all that. So if I want the derivative, that's how I figure it out. Now, this leads us into this definition. This is the one we are going to use. The Laplace of t to the n times a function is equal to negative 1 to some power of the n times the nth derivative of our Laplace transform. All right, let's get a few examples. I wrote that at the top here so we don't have to scroll back and forth. This beginning one here. All right, so we have this exact function. So what I'm going to do is, I know that e to the 3t, you're like, I don't want to do that yet. So what we could actually do is write this out. Negative 1, okay, the power to t is 1, so it's to the first power, times the first derivative of the Laplace of e to the 3t cosine 2t. So I just followed the formula first. We actually really don't even need that bracket. That's just following the formula. Right? I'm not even worried about the Laplace yet. Okay, so I get a negative, because negative 1 to the first power is a negative, ds, and then we take our Laplace. Okay, Laplace, okay, I got that e to the 3t, which means that I just focus on this. If we go back and look at our rules, I focus on this, and I replace t with t minus 3, or s minus 3, rather. So the normal one was s over s squared plus 4. That would be just this. But because of the e to the 3t, we get s minus 3 over s minus 3 squared plus 4. All right? And then unfortunately, here we have a quotient rule. So it's going to be negative, leave that outside, low s minus 3 squared plus 4, low d high times 1 minus high d low. That gets us 2s minus 3 to the first times it's a chain rule, which will give us a 1. And then over s minus 3 squared plus 4 squared. Right, I'll let you figure out all that algebra. What you're going to end up with, if you would like to work it all the way down, is we get s minus 3 squared minus 4 over s minus 3 squared plus 4 squared. So we just simplified the numerator. I'll let you do that. It's just algebra. All right, we are going to do one last thing here. It's compute t times the second derivative. First thing I'm going to write is let the Laplace of y of t equal y of s. All right, so the Laplace of t to the first times y double prime. If I follow the rule, this is negative 1 to the first times the first derivative with respect to s times the first derivative of the Laplace of y double prime. It's following the formula. All right, I got negative 1 to the first, it's negative d ds. And then the Laplace here is going to be s squared times big Y of s minus s times little y of 0 minus y prime of 0. So we get negative d ds. I'm going to go ahead and simplify everything in here. S squared times y of s minus what was y0. Oh, we don't have it, so I'm just going to leave it. Minus, I guess we didn't need to write it again then, so I'm going to erase that. I apologize. We're going to take the derivative now. It's negative. And then this is a bit, this is where my students mess up. Just misleading. Y of s is a function of s. So if I'm taking the derivative of s, I got to take the power rule here. So 2s times big Y of s. Plus I leave s squared alone. And I take the derivative of big Y of s. I don't know what that is, so I'm just going to call it y prime. Y0 is a constant, so the derivative of s is a minus 1. Derivative of this constant is going to be 0. I could distribute the negative 2s times y of s minus s squared times y prime of s plus 1. Okay, so that's it. That's how we take our derivatives of a Laplace. Like I said, this stuff gets really difficult because it is just pattern recognition, which means it's a lot of staring at the table and trying to ask yourself, how does this apply?